Hello everyone, let's start with the problem count the parts. This problem is from Geek for Geeks and let's read out the problem. It is saying given a directed acyclic graph which is basically known as tag with V nodes labeled from 0 to V minus 1 and a list of directed edges. Okay, count the total number of distinct paths from a given start node to a destination node. Okay, we need to count number of distinct path. Got it? Each edge is represented as edge of I uv, indicating a directed edge from u to v. Okay, so let's understand. This is the edge they've given and this is diagram, and there are 4 nodes basically, 1 2 3 4, and source is 2, destination is 3. So let me go to the board and explain you. So here they're saying V is number of nodes, which is 4, which are 1 2 3 4, and edges they've given in UV format. This way, let's say this is an edge 2 comma 0. It indicates there is an edge from 2 to 0, and it is directed. And you can consider this way also. Second is like 2 comma 1, and you can take 0 comma 1. These are edges, and 0 to 3. And 1 2 3. So these are all edges, adjacency list they've given. So we need to find number of ways from source node to destination rows to reach with a distinct path. Okay, one, if you see, you can reach from 2 to 0, and from 0 to 3, this is one path, and other path will be 2 to 0, and 0 to 1, and 1 to 3. This is second path. And if you see the third path, 2 to 1 and 1 to 3. So 3 paths we can find here, 3 distinct paths. So how can we solve this? If you see, we can solve in this way. Like, see, what we'll do is we'll do a DFS traversal. Why DFS traversal? We can do BFS as well, but let's follow DFS. Why DFS? We are doing depth first search. So from 2, what we'll do is first we'll convert this edges to adjacency list. How can we convert this? See, 2 is the edges, and which are all attached to 2. From 2, if you see, 0 is, we can go from 2, you can go to 1. 2 things. Okay, now let's take 0. From 0, where you can go, we can go to 3, you can go to 1. From 0 you can go to 1, and then 3. So 1 3. Next let's take 1. From 1, where you can go, you can go to 3, only 3. And from 3, where you can go, you cannot go to anywhere. So 3 will not come into picture here. So this is the thing. This is adjacency list. So in DFS traversal, what we'll do is we'll traverse from the source node, which is 2 here, and we'll go to first node in this adjacency list. This is basically adjacency list. So we'll go to first one, so which is basically I'm going from 2 to 0. Here I went, and I'll keep one visited array of size v, which is 4 in this case. V is 4 in this case, and which will be initialized to false initially. Whenever I'm going to 2, that will be initialized to true, this visited array, and we'll go to the its adjacency list. We're going to, let's say, 2 now. Now we'll mark this visited as true, and we'll go to its adjacency. Here it is 3 and 1. We'll go to 3. Whenever we encounter 3, we'll return 1, meaning we have got one path. So this will return 1. Okay, so now 3 we have come, and then we'll have to go to next adjacency list. From 0 we have 3 and 1. So we're going to, let's say, 1 now. This is not visited, so we'll mark it as true. Now we are visiting it, and then from 1, where all we can go, we can go only to 3. So from 1 we can go to only 3. So whenever we get 3, we're returning 1, because which means we reached the destination. So we'll return 1 here. We have written 1 here, 1 we have written. Okay, now since this is the path we are traveling, this path we have traveled, we have went here, came back, and then this path we have explored, went here, came back. Okay, now so this from 0 to 1 we have called, it will go back. How it will go back? It will give the value as again 1. Okay, from here it is getting value 1, from here it is getting value 1, which means it will be added 1 plus 1, which means 2 path. So as you can see clearly, from 2 it will go, from 2 to it will go 0, 0 to 3, and then 0 and then 3. So this is 2 paths. So from 2, as you can see, 2 paths we are getting. So in that way, so it is returning 1, and it is returning number of ways it has got. Okay, so it is 2. And then next call will be to this function, this node, and since it is already visited, we will take one distance vector. Okay, distance vector also, its size will also be of v only. So whenever it is true, we basically store the values, these values in the distance vector. So whenever that node is visited, we'll simply return those values. So in this case it will be returning 1, and this will be returning 2. So 2 plus 1 is 3 basically. So which is our answer for this one. Pretty much I think you got what I'm trying to do. Let's try to understand this second example. So that is second example. So again, what we'll do is we'll keep distance vector. Okay, distance, here we have v is equal to 4. We'll take it here, let's say v is equal to 4, distance of 4, which will be initialized to 0 0 0 0, and visited vector of your size 4, that will be initialized to initially false. Okay, so now we'll start with source. Source is 0 and destination is 3. So whenever we are starting with 0, let's say we are starting with here, so now it is marked as false. So this is 0 index, 1 index, 2 index, 3 index. So 0 is marked as false, we'll mark it as true, and from here we'll call to its adjacency list. Okay, so we called 1. 1 is also marked as false, so we'll mark it as true. We'll mark true, and we'll call it adjacency. This is marked true, this is marked true, we are calling it adjacent. So now 2, as you can see here, it is marked false, we'll mark it as true, and we'll call it adjacent. Whenever we got node is equal to destination, so in that case we'll return 1. So 1 we are returning, 1 way is fine. So 1 way is found, and this function will return back again in DFS. So this will return 1, and since from this node we have called this function is this node is left out, so we are calling this node now. So whenever destination is here, node equal to destination, will return 1. So 1 plus 1 is 2, and this will return it as 2. So as you can see, for this we have only 2 paths, which are those from 0 to 1, 1 to 2, 2 to 3, and one more from 0 to 1 and 1 to 3. So these are the 2 paths, 0 to 1, 1 to 2, 2 to 3, 0 to 1, 1 to 3. So 2 paths we are getting. Okay, so let's try to write the code. So what we'll do is we have got adjacency list, edges. We'll have to make adjacency list. So let's take vector adjacency list of size v. We'll iterate through these edges. Okay, and since it is directed, so it will be edge of 0 to edge of 1. You're getting, this one is like starting node, and this is the ending node from pointer, like from 0 to 1. So this is adjacency, edges of 0, this is edges of 1. So adjacency list we have got. Now we'll take vector boolean visited array. Okay, and which will be initialized to false, which whose size is 0. If you don't even put here, let's say false, by default it will be false only. Now we'll take distance vector whose type is integer. This is okay. Now we will return DFS. In DFS, what will be passing? Will passing source, destination, adjacency list, visited vector, and distance vector. these three things. Let's write the function for this. So DFS will return the integer. First one is node, second one is destination. Let's pass it by reference so that no copies will be made of that, whose pointer address will be basically returned in every whenever you, function we call, that will be called with the pointer, I mean it's their address. And next is our adjacency list. Let's pass by reference only, we will not make copy of that. Next is visited array, so boolean. Let's pass it by reference only, because whenever in future one node is visited, and let's say we are trying to visit the same node one more time. So in that case, if we not pass by reference, its value will be lost. So we are passing by reference. And distance. Okay. Distance also, let's pass it by reference only. Now we'll say if node is equal to destination, which means we have reached a destination. So in that case we'll return 1. If we are not reached destination, we'll mark visited of node as true first. We'll take one count, which is number of ways, number of paths basically. We're taking adjacent nodes, basically from particular one node we'll be traveling to its adjacent nodes. Basically what I'm trying to say is that, let's say 0 to which one, let me consider this first one. 1 is a node, its adjacent nodes are 2, 3. So we'll be traveling to 2 and 3 in this way. And if not a visited of adjacent node, if adjacent node is not visited, which means we'll have to visit that node, so that we can find out number of ways to reach that path from the destination. So here it will be adjacent node, destination, adjacency list, visited, destination, distance vector. Okay, if let's say that node is visited and you are visiting one more time, so we'll be storing that number of ways to reach that node from the destination, that will be stored in the distance vector. So we'll take that value from distance vector. So how we are storing that? We are storing here, return distance of node is equal to count. So whenever we are returning, we are storing that value in adjacent, I mean distance vector. So in future, whenever we got the same node, so we can do it, take from the distance vector. So let's try to run the code. It is running fine. Let's try to submit the code. Yeah, it got accepted. So this was the problem. And if you try to analyze the time complexity of this algorithm, so we are taking this one edges, let's say it has m of m size, so it will be O of m. And if you're calling DFS, so DFS at max will be going to the v vectors. Okay, so v vector, and then if you see here, it is every time it is calling for its adjacent nodes, which is e, so it will be v plus e. It will not be v star e, because once that node is visited, we are keeping track of that in visited vector. So from there on, we don't again go to the same paths. Once node is visited, we are keeping that number of ways from destination to that node in a distance vector. So we will be returning from that in O of 1. So it is v plus e. And space complexity, if you see, this is adjacency list we are creating, so actually it should not be counted here, but let's say we count it, because instead of edges, if adjacency list is given, then this will not be counted, but now let's count it. So it is v plus e edges, and the stack space here will be V. So basically V plus C space complexity. So thank you guys for watching the video.